Ready?
Hi, so welcome to a beginner's guide to Cassandra. I'm Kim, and I work for myself, which essentially means I can even call you? If anyone can.
Just keep on talking.
So I work for myself, which essentially means I get to make games for the fun of it. But I finance that through doing freelance Java development, mainly server-side work for social and mobile games companies. So these are some of the games I've worked on. I first began to use Cassandra when I started working on Monstermind. And I realized because of the number of interactions we have with the server, every time we also share a game on Facebook, that we just wouldn't be able to manage with the traditional relational data store and the use cases that I'm used to and how to model that. So we're looking for a better solution. We've got sound. And so I investigated a couple of different options, and we chose Cassandra to use with Monstermind. And now you don't know who I am. I'll hand over to Tom.
Hey, my name's Tom. I've worked on projects ranging from online advertising to online games with Kim. I'm currently building and managing the infrastructure for Bossa Studios and their range of online games.
So I think the first question we want to ask ourselves is, what is Cassandra? So it is a NoSQL data store. And I think a common misnomer is that NoSQL is one thing. So one NoSQL data store is similar to another. But they're not. They're actually really, really different. There are three main types of NoSQL data stores. There's a document one, where the central concept is a document that's normally encoded in a standard format. And some examples of these are Mongo or CouchDB. You get a graph data store where relations are well represented as a graph, and this helps you traverse associative data sets very quickly. So an example would be like a social network or something like that. An example database is Neo4j. But where Cassandra falls in is as a key value store. And it's where you store your data in a schemaless way. There are many different types. Cassandra is considered an eventually consistent one. I'm not a huge fan of that term, mainly because it initially put me off Cassandra. When I heard eventually consistent, I pictured my Twitter feed where I post a tweet and I might not see it for a couple of minutes. And I wanted my data to be more consistent than that. However, the consistency in Cassandra is tunable, so it was suitable for my needs. So Cassandra was developed by Facebook and open sourced in 2008. It was based off the Dynamo and Bigtable white papers. So from Dynamo, it took partitioning and replication and the log-structured column family data model from Bigtable. It's used by a number of big players, such as Netflix, eBay, Twitter, etc. And it's mainly supported by DataStax. It is an open source project, so you can check it out at cassandra.apache.org. Yeah.
So what are the reasons you use Cassandra? To me, there's four big advantages. The first is speed. Reads are very fast. Writes are even faster. So if you model your data nicely, you can easily do 1,000 reads a second per node and 10 times as many writes. Network Walls has a good article detailing sort of a comparison between different NoSQL data stores. So yeah, here you go. That's an insert-heavy workload. Cassandra coming out second best. That's a mixed load, again second best. And that is a read-heavy workload with Cassandra in third place. Don't look at the comparisons as which database is better or which database is worse, because they all have very different use cases. It just shows that Cassandra, if it fits your use case, it's a very capable data store with regards to speed. The next big advantage of Cassandra is availability. It's very fault tolerant. It's got a shared nothing peer-to-peer architecture, which means there's no master components to be single points of failure. So far, in my experience, I haven't managed to lose any data on my Cassandra cluster despite node failures. And even if I had, the on-disk storage is very simple to back up. The third big advantage is scalability. If one node will do 1,000 reads, 2 nodes will do 2,000 reads, 3 nodes will do 3,000. So it'll scale linearly with the number of nodes you add. The fourth big advantage is a community. It's got a very active community and some big players behind it, so it's easy to get help and advice if you need it.
So Cassandra isn't a panacea, and it's not just going to cure all your woes. There are some disadvantages to it. And the first one, it is relatively young. I mean, it was only open sourced in 2008. But please don't mistake maturity for stability. I've been using Cassandra in production since version 0.8. It's now on 1.2.3, and I've never had any issues or lost any data, nothing related to the stability of Cassandra. However, where we have had difficulty is trying to recruit people with Cassandra expertise. Because it is so young, there's just not that many people out there looking for jobs that have that knowledge. And so we've really had to invest time in learning Cassandra from the ground up. And unfortunately, there are not that many skills or not that much knowledge you can take from a traditional relational database and apply to Cassandra. So you really need to invest the time in understanding how Cassandra works and how it works underneath your basic data structures in order to build up a proper performant data model and to use Cassandra successfully. There's also a lot more responsibility for the developer. So I'll get into this a lot more detail when I go through data modeling for Cassandra. But yeah, there's a lot more on you as the developer to get right. And you know, all the normal nice goodness you get with transactions, things like rollbacks and independent operations and things like that, you don't get them with Cassandra. And so depending on your use case, you've got to look at ways to come around that. And I'll go into that a bit more later. And then there's another thing called repairs. Now, it's not actually a negative thing to do a repair. It's just a piece of maintenance that you should do approximately once a week, where you run a repair on each of your nodes, and it ensures that your nodes are consistent across the cluster. So it's just a bit of extra maintenance to make sure that you have a run. And finally, there used to be an issue with scaling under load. So if you were under load and suddenly needed to scale up, it would initially actually add more load to your cluster. However, with the introduction of virtual nodes, this is no longer an issue. So as long as you've enabled virtual nodes, you don't need to worry about it.
Okay, so the token ring is how Cassandra distributes rows across your cluster. It takes the key that you've given to the row, you converts it to a murmur hash of the key, and then uses that to find its position on the token ring. So in this example, if A were to hash to 4, for example, it would land on data range 1. And if B were to hash to 70, that would land on the node responsible for data range 3. On top of the token ring, you've got replication strategies and snitches, which are responsible for how your replicas are distributed across your cluster. The strategy defines how the replicas are distributed. The snitch tells the strategy about your physical infrastructure. So in this example, this is a simple strategy and a simple snitch. Row A is replicated across nodes A, B, and C. And row D, for example, is across nodes D, A, and B. This gives excellent fault tolerance. In this scenario, you could lose 2 nodes and you probably wouldn't have lost any data. It might mean that you are no longer able to do reads and writes, though, because there are certain requirements for consistency, but we'll go into those a bit later. This example, like I said, is a simple strategy and a simple snitch. You get much better strategies. You get a network topology strategy and an EC2-aware snitch, for example, which would route replicas to different data centers on Amazon. So that way you could be sure you're redundant even if a data center in Amazon goes down. So virtual nodes, which Kim mentioned earlier. Before Cassandra 1.2, contiguous ranges of the tokens were stored on each node, which was quite inefficient for repairs and for scaling because only the number of replicas could take part in those operations. So if you had a replication factor of 3 and a 30-node cluster, 90% of your cluster was sitting idle while those operations were happening, which is why, as Kim said, scaling was quite an expensive operation. vNodes means that each node gets its token range sliced up and then shuffled around the cluster. So through some clever tricks, this means that every node can take part in the repair and scaling, which puts far less load on the cluster. It's not enabled by default on Cassandra 1.2, but unless there's a good reason not to, turn it on.
So let's look at the actual structure of a data store. So you start off with your cluster, which is the actual physical machines or the nodes in a logical Cassandra instance. And a cluster can contain multiple key spaces. A key space would be analogous to a database in a relational database. And it's on the key space that you set your strategy and the replication factor that Tom was just talking about. And key spaces are a namespace for column families. So a column family would be similar to a table. They contain a number of rows, and each row has a key and a number of columns. But try not to think of the columns as you would in a traditional relational database. Instead, think of the columns as a name-value pair. So you could think of a column family as a sorted map, where the key is your row key, and the value is a sorted map of name-value pairs, which are your columns. So here's an example. This would be referred to as a static column family. So here I'm storing data about employees. You can see on the left that I've got the employee ID, which is my row key, and then on the right the column value pairs. So one important thing to note is that each row can have a different number of columns, and it can also have different columns. You can define some of the columns up front, but you don't need to at all. It can be completely schemaless, and you can just define the columns as you go. So to try to get away from thinking of it as a relational database, I've represented this row in JSON, and there is some metadata associated with each column. So there's a timestamp here, which I'll come back to, and there's some extra functionality that can be added. For instance, you can have auto-expiring columns. But let's look at a better example for Cassandra. So this is more of a dynamic column family here. So what I'm modeling is a car tracker system. So our row key is the number plate of the car and the date that the data was sent. And then as the person drives around in the car, every now and again, the tracker is going to send our system the GPS coordinates for that car. And so I've put in some data here. My column names are actually the time I received that data or the time that data was applicable for. I've represented it just as a normal time here for readability, but you'd probably want to use something like a time UUID in a real application. So now what happens is if someone's car is stolen, you can say, okay, I've got the number plate and the day and the approximate time, and then you can query a range of columns around that time to see where the car has traveled to, where it's going, and to actually be able to track and follow the car. Now, an important part of this is the ordering of the columns. It's very, very important in Cassandra, and the column ordering is determined by the comparator that you set on the column family. So here it is ordered by time. And it's really important because when you do reads from Cassandra, you want to read contiguous columns of data. You don't want to read a couple of columns here in the row, and then later in the row a couple of columns over there. And this is for performance reason. The comparator gives you efficient access into the data by minimizing your disk seeks. So here we're just adding columns as we get more information from the tracker system, but there are some limitations to how many columns we can add. So Cassandra's hard limitation are a maximum of 2 billion columns per row, and all data for a single row must fit on the disk of a single machine. However, I'd go further and say actually all the data for a row should fit in memory. So you're probably looking at millions of columns instead of billions. Now there's a common use case, and I said I'd come back to those asset properties later, and that's when you want to count something. So for example, when you're doing a game, it might be your XP and your in-game currency, where you don't want to set it to specific values. Instead, you just want to increment it or decrement it. And Cassandra realized that this was a very common use case, and so it actually provided support for it in the form of counters. So counters are a special type of column. They're a 64-bit signed integer, and you can do an atomic increment or decrement on them. They're very limited in the operations you can do, so you can literally increment it, read it, or remove it, and that's it. The other thing is you can't make counters with normal columns in a normal column family. When you define a column family, you'll define it in sets of type for counters, and then it will only contain counters. There's another type of column family called a SuperColumn family, which may look super. Now, one of the key cornerstones of data modeling for Cassandra is to denormalize your data, and this looks like a good way of doing it. A supercolumn essentially is a column which contains multiple columns. And once again, these are all dynamic as per normal columns. And it may look super, but it really isn't. They don't perform well at all, and please do not use them. I'm mentioning it because if you use Cassandra, you'll come across supercolumns, but don't use them. There's a much better solution now, which is called Composite Columns. And this is where we flatten out those supercolumns, and it uses a comparator that is made up of multiple comparators, and then the column name is actually made up of different components. And then the comparators sort on the different components of the column name. So you get the same flexibility you do from the supercolumn family. In fact, you get even more flexibility because you can nest to an arbitrary level. But you don't get any of the speed and performance disadvantages of a supercolumn family. It also helps you group otherwise static skinny rows into wider rows for greater efficiency. And as custom inverted search indexes, when you want more control over the column family layout than a secondary index would give you.
So when you're reading up about Cassandra, you'll probably hear a fair bit about the CAP theorem. It states that in a distributed system with reasonable latency, you can only choose two properties out of consistency, availability, and partition tolerance. Cassandra gives you availability and partition tolerance, and lets you choose your latency by tuning your consistency. So when the client's writing data, you get to the client gets to select how consistent they'd like their data to be. So as an example, you can choose between a consistency level of 1 or a consistency level of all. If you choose 1, the quickest node to write the data will return to the client and say success. If you choose all, then it'll be the slowest node to write the data. Kim will explain further on the next slide.
So there are a couple of main consistency levels for Cassandra. Any means that Cassandra will return to the client once it's heard from any node. 1, 2, 3, etc. is once it's heard from that many nodes, it will return to the client. Quorum is a very interesting one because what quorum means is more than half. So approximately half plus 1. So if your replication factor was 3, quorum would be 2. And if your replication factor was 4, quorum would be 3. So when you're reading or writing at a level of quorum, it'll wait for more than half the nodes that should be involved to return to Cassandra before it will return to the client. You get local quorum as well, which means it wants to achieve quorum on the local data center, or each quorum, which means it must achieve quorum on each data center. And all means it waits for all nodes to return. So let's look a bit closer at this with some examples. So over here, I've got 3 nodes, and my replication factor is 3. And I've got a bit of data represented by the blue dot. So let's do a write at level 1. So we send the request off to Cassandra, and Cassandra then, or the coordinator node, will then tell the nodes, we're writing at level 1. Node A successfully receives the data and returns yay to the coordinator node. The coordinator node will return to the client saying, okay, write was successful. But it's possible that node B and C didn't receive that data. So in the worst case scenario, you might only have one node with the new data on it. Then, if you read at level 1, you could potentially get old data or new data. If you read at level quorum, once again, you can't guarantee that you'll get the new data. You could get either the old or the new data. But reading at all would guarantee that you get the new data. Now, what's important to note is that when we do the write at level 1, we're not saying write to one node. What we're saying is write to all the nodes, and as soon as one says it's successful, then return. So chances are that it could have written successfully to all 3 nodes, or there might have been a glitch, a node might have gone down, something might have happened, and it's not guaranteed. So let's look at an example with quorum. So if we write at level quorum, we're guaranteeing that at least 2 of our nodes will be updated with the new data. If we read at level 1, we could get the old data or new data. But if we read at level quorum, we're guaranteed to get the new data. And all would naturally return the new data. So what's important about quorum is that if you both read and write at quorum, then you can achieve consistent data and still have some tolerance so that if one node goes down in this example, you would still be fine. Cassandra would still be able to return and operate as normal, and it wouldn't affect your application at all. So your tolerance is determined by your replication factor minus quorum. So I said if it reads at quorum, it would have the right data, it'd have the correct data. But how does it know? Because it could have had the data returned from node A and node B. And this is where that timestamp comes in. So it would receive the data from the 2 nodes, and it would see, oh, one's got a more recent timestamp than the other, and that is the data that it would send to the client. And finally, if you write it all of them are guaranteed to be updated, and reading at any level means that you will get the latest data. However, if even one node goes down, that's it. Cassandra can't, it can't then read or write at all, and your application will start having issues. So it's not really a good plan.
So one thing Cassandra had to deal with was distributed deletes, because in an eventually consistent system, that's really tricky. You need a way of making sure that all nodes know about a delete before you properly delete the data. So in this example, if node 3 were down and a user deleted the row with the key user 1, node 3 comes back up, and when Cassandra repairs itself, that deleted row is replicated back to the nodes that it was successfully deleted on. So the way it deals with this is something called Tombstones. Instead of deleting the whole row, it just deletes data out of the row. So if node 3 is down when it deletes, when node 3 comes back in, using the timestamp Kim mentioned, it can see that the delete is more recent in the data, and it replicates that across to all the nodes. The old row, there's a similar technique used for deleting single columns. It's also used as a timestamps. And these are cleared out every 10 days by default. Which is why you need a weekly repair to make sure that the entire cluster knows about your deletes. So
we're at a Java conference, so it's probably worth, mentioning the Java libraries. So when Cassandra was first developed, you used to access it through a raw Thrift API. That was the way of speaking to Cassandra from your client. And I don't know if any of you have worked with Thrift, but it's quite verbose. It's not very fun to work with. It's very clunky. And so very soon there were some client libraries being developed for it. And the predominant one in the early days was Hector. Now the Hector developers had worked with Thrift a lot, and they built the API on top of this. And it was built thinking of Thrift rather than thinking of a database. So quite a few people used it, and they found it a bit clunky, a bit difficult. It wasn't the way they would have structured an API, and you got different spin-off projects from that. And they had perhaps wanted to achieve different things from it as well. However, Hector soon realized this, and they completely changed the way you access Cassandra from Hector. So if you went and used Hector now, it would be very, very different to how you would have used it a year or two ago. But some of the spin-off projects, so SteerNax was developed and open sourced by Netflix. And there are a couple too many to mention. In fact, there's even more than I've put on the slide here. But there has been an important recent development, and that's that you can now talk to Cassandra through a binary protocol. And what Cassandra really wanted to do was to be able to build something that would be more like a JDBC driver that we used to. And so they developed the Java driver. And so instead of talking Thrift, the Java driver talks CQL. I always want to call it SQL, and then I get very confused. But it's CQL. And it's a lot faster than talking Thrift, and you can prepare statements. And Tom's going to show you a little bit of it now.
So every database should have a command line interface. Cassandra used to use Cassandra CLI exclusively. There's a new one called CQLSH, which is the one to use unless there's a good reason not to, because Cassandra Query Language is the way Cassandra is moving towards for speaking to it. So you can see in the example here some examples of CQL. Don't be fooled by how similar they look to SQL, because in some ways they are, but in a lot of ways they're not. So yeah, just read up about it and make sure you understand it.
So now on to possibly my favorite topic, or possibly the topic that makes me want to tear my hair out the most, and that's data modeling. So if I could stress one thing today, it's know your data access patterns before you model your schema or your data store. And there's a good reason for that, and that's because you want to write together what you read together, or you want to read what's been written together. So as I mentioned previously, you really, when you do a read from Cassandra, you want to read contiguous columns rather than some columns here and some columns further down the row. Similarly, you only want to read one row at a time. And the way you get the data together, there are two methods. One is to know your comparators. So make sure that you choose appropriate comparators. And please use composite columns. So use those comparators of comparators to achieve the appropriate ordering for your data. And the other way is to denormalize and duplicate your data. So it's very different from how you would normally design your database in a relational database. And we'll look at some examples. So if any of you have ever played a social game, you'll probably be familiar with the friend bar. It's a very common use case within the social games industry. And essentially at the bottom of your game, you've got a list of all your friends who are playing the game and a bit of information about them and the game. So in my happy social game over here, I've got the profile picture, I've got their name and the level they've reached. Now, just for a minute, let's imagine that we are using a relational database and how we could possibly model this data. So I've created 3 tables here. I've got a player table, which stores information about the player, personal information. This is where their name and their profile picture URL is. I then have a friends table, which models the relationships between different players. So it says if player A is friends with player B. And finally, I've got a game data table, which has data specific to the game or the gameplay, and this is where my level information is stored. So if I want to get all the data for that friend bar, I need to join these three tables. And just looking at it, if you've got 10 friends, over the three tables, it's 30 rows. 1,000 friends is 3,000 rows. And you might think 1,000 friends is a bit ridiculous. I mean, how many friends do people on Facebook actually have? But I've worked on a social game where just on a single shard, one player had over 1,500 friends. Which brings up another issue. If you're using large amounts of data, large data sets, you're going to have to shard that data in a relational database. And then you lose out on all your joins and the cool things about relational databases anyhow. And that'll just add to your performance problems. But now let's look at how we might do it in Cassandra. So I've created a friend bar column family here. And what this means is that every time I want to load that friend bar, it's just a single read from a single row. That row contains all the information I need for that friend bar for all my friends. And that's where Cassandra is great, because you can just expand as a person gets more friends. You can just add more columns on. And here I've used Composite Columns. So my column name is made up of an ID for the friend, as well as the information it contains. Now this may sound all well and good, but you're probably thinking, yes, but we have to maintain that data. And this is where I mentioned earlier it's more responsibility for the developer. So yes, when a player levels up, you do have to write not only to the column family, which is keeping the information about that game for that player, but also to the friend bar column family, and you've got to write to that for every single friend that that player has. But in Cassandra, writes are a lot faster than reads. The same thing happens for name and profile changes. But let's just for a minute pretend that Cassandra writes and reads were equal. Well, how often does this information change? So initially, a player might level up a couple of times in a game session, but pretty soon it'll be only every couple of game sessions. The name and profile picture should hardly ever change. So you're looking at the information only being updated once every couple of game sessions. Whereas, how often do you load the friend bar? It's every single time they play, and you might refresh it during the game session. So you're looking at least once every game session. So that's once a game session for read, and once every couple for write. And then also think about it, for that read for 1,000 friends, we had to read 3,000 rows. For here, we'd be writing for 1,000 friends, 1,001 rows. One for each friend's entry in the friend bar, and once for that actual player's game data. So it's worth thinking about different ways of modeling data, even if you're not using Cassandra and you don't have the right speeds that Cassandra gives you. But let's look at an anti-pattern. So I love the Q anti-pattern, mainly because it looks perfect for Cassandra. You've got this flexible column layout. Every time you get a new job, you can just write it on, create a new column with the time that it was created, perhaps some information about the job that needs to happen. You have lots of write, makes excellent use of the comparator. So why is it an anti-pattern? Well, remember what Tom was saying about how Cassandra does its deletes? So what happens? Your job runs, you write some entries, you've got another process, say, that reads them out, does the job, and then deletes them once the job's complete. But doesn't actually delete them. Instead, it tombstones them. So initially, the queue is very quickly, and then more jobs are processed, and more are tombstoned. Now, it's by default every 10 days that those are garbage collected, which means that after a week or so, how many entries will you have against that row? And what happens when you go to read the first few? Cassandra then has to scan through all these tombstone columns to come to the first one or two. So this, I think, really highlights why it's key to really get to know Cassandra and understand it and play around with it and do testing when you do your data model, and not just try fit something you've got in your head from, say, a relational or another space into Cassandra. So just some final thoughts. Once again, know your data access patterns. Be careful of JPA. So there's a reason I say this, and the reason is that what I see very often is people design their domain, it's beautiful OO domain, very similar to what you'd design for a relational database, and then they map their database to that domain. And if you do that in Cassandra, I know because I've done it, you're going to have a poor system that performs much worse than any relational database out there. What you really need to do is to look at those client patterns, see how the client's accessing your data, and code to that. And it means a lot more work, and it means when the client changes stuff, you should change stuff. And that initially was a bit funny for me because I wanted to develop the system that was completely independent of the client. But to get the best performance, you really, really need to know how your client's accessing that data and how that data will be brought out. If you want to code like a relational database, don't use Cassandra, go use a relational database. Cassandra is great and it's got some awesome things, but you really need to respect it and treat it well. And finally, there's so much more we could go into on data modeling. I could speak the rest of the day on it. But everything's online. There's a lovely tech blog on eBay where they've spoken about some good design patterns. So please do go check it out. We will have a list of all the links and a URL where you can access them later.
Okay, so Memtables are Cassandra's in-memory data structure. As you can see, there's the row key, there's multiple column names, multiple column values, and then there's metadata like timestamps. Now, the example I've thrown up here is another example of an anti-pattern, something you should never use Cassandra for. In this example, we're writing the last time we saw someone in our application. So, yeah, I'll show you why this is a bad idea in the next slide. So SS tables are Cassandra's on-disk data structure. They're append only, which is why the writes are so fast, and they use some really clever tricks to minimize seeks, which is why the reads are so fast. As you can see, if Kim were online for 2 minutes there, every 30 seconds we're updating her the last time she was online. On disk, it starts to spread out very quickly. So it's append only, so you get a new entry each time we write to the database. That is cleaned up periodically, but you can't rely on when that cleanup will happen. So effectively, as your data gets used more and more, it takes longer and longer to seek through the old timestamp records to get to the one that has the current timestamp, which is or the latest timestamp, which is your active data. Cassandra can handle fairly fast-moving data, but the trick is just not to store it all together in one row. And that's it.
So these are some of the links that we've had throughout the presentation, but Tom's kindly put them all on his site. So if you go to tomvn.com, there's a post there with all these links in them, so you don't actually have to write them all down. We've got about a couple of minutes, so does anyone have any questions? Oh, sorry, yeah. Yes? So I think with that example that Tom was showing, if you do something like that purely per time, it means that during that time period, every single write is going to go to that node and it's going to be written there. But if you split it, if you're able to split it on something else as well, then that's going to be spread more around the cluster.
Well, another trick in the last scene example. Sorry, I should repeat your question. You asked.
Yes.
Can you repeat your question? Yeah. Okay, so you. Got you. So you asked you asked about how good Cassandra is with fast-moving data and how you could partition it to take advantage of it. Like I said, as long as you're not storing your fast-moving data from multiple sources on one row, it's very good. So in my example, the easy way is to store a last seen with an individual user object, because then it's only that last seen for that user that's changing on that row. Logs, you'd probably want to store. I mean, logs tend to be append only, right? You're not going to be reading them back very often, and the reads are where it's going to suffer if you've overwritten lots of the same columns. So those you depending on how many logs you're getting, you just bucket them up by say day as your row key, and then just start whacking columns in. Yeah, it would work very well. Lots of people do use it for pretty fast transactions, like analytics and stuff like that.
Yep.
Okay, so you've asked about the peer-to-peer architecture of Cassandra. If you write a record at consistency all, how does it know once all the nodes have completed? So in the Cassandra ring, your client can connect to any of the Cassandra nodes, which then work out, based on that hash that I showed you, work out where on the ring your replicas live. And it forwards the query onto those nodes, right? And then based on your consistency, or the query is forwarded onto all the nodes, but based on your consistency, when enough nodes have responded and said, here's the answer to the read, or I've successfully done the write, then it'll return to the client and say, complete. Does that answer your question?
So which node knows about the next one?
They all know about each other. They've got a gossip protocol, which as you add new nodes in, they kind of all talk to each other and update each other on which nodes live at which token ranges. So yeah, they all know about each other. That's how.
Any more questions? Else, I think we can break early for lunch. I think we're just 5 minutes early for lunch.
Score.
Great. Thanks.
Thank you.